As everyone knows, there's nothing in the world that can't be compressed. It's just a matter of forcing molecules and atoms closer together. Even if there's only a single atom, in theory you could squeeze its outer electrons into the atomic nucleus. And if the mass is large enough, you wouldn't even have to do anything, it would compress itself. For example, it could become a neutron star in a neutron degenerate state. So can a neutron star be compressed even further? Of course it can, there's nothing that can't be compressed. But once the barrier of neutron degeneracy pressure is broken, in theory there's no known force left that can stop matter from compressing further. At that point, matter would be compressed infinitely, all the way down to a single point. That point is what we call a singularity. In general relativity, the center of a black hole is a singularity. Of course, this refers to a static Schwarzschild black hole. But real black holes are all rotating Kerr black holes. Early on, people believed that because Kerr black holes have angular momentum, their inertial centrifugal force might, to some extent, prevent a singularity from forming. So singularities, they thought, probably wouldn't exist in reality. However, Penrose later proved rigorously, using mathematics, that within the framework of general relativity, once an event horizon forms during black hole formation, a singularity must exist. This is known as the Penrose singularity theorem. Based on Penrose's theorem, Hawking later extended it to the entire universe, meaning the universe itself must also contain a singularity. This is called the Hawking singularity theorem. Put these two together, and you get the famous Penrose-Hawking singularity theorem, often just called the singularity theorem. The singularity theorem shows that, within the framework of general relativity, as long as a few core conditions are met, like causality holding and positive energy density, then a singularity must exist. But for real, rotating black holes, what's inside isn't a point, but a ring, called a ring singularity. Whether it's a point singularity or a ring singularity, neither of them is a three-dimensional structure. So in theory, a singularity has mass but no volume. That means its density is infinite. Okay, once infinity shows up in physics, that's a sign that something has gone seriously wrong. In reality, aside from the universe itself, which you might generously assume could be infinite, there's nothing else we can legitimately treat as infinite. So does that mean the singularity theorem is wrong? Notice what we said earlier. The singularity theorem is based on the framework of general relativity. At the core of general relativity is Riemannian geometry. In this framework, whether it's spacetime or matter, everything is continuous, smooth, and infinitely divisible. But quantum mechanics tells us the real world isn't like that. Whether it's energy, momentum, or position in space, none of them can be infinitely precise. And if something can't be infinitely precise, that means the real world has a minimum resolution. On top of that, the uncertainty principle proves from another angle that something infinitely small simply cannot exist. For example, as you compress something smaller and smaller, quantum effects grow stronger and stronger. When they become strong enough, quantum fluctuations become impossible to ignore. At that point, the smooth spacetime of general relativity no longer holds. The theory breaks down right at the singularity. In other words, what the singularity theorem really tells us is about the limitations of general relativity, not that singularities must actually exist. In fact, on this issue, almost all physicists believe singularities simply cannot exist. They're just a mathematical limit, an illusion that appears when we ignore quantum effects. In the real universe, although general relativity works extremely well in most situations, inside a black hole, under such extreme conditions, gravity shouldn't be described by general relativity anymore. It should hand off the baton to quantum gravity, and quantum gravity is basically the holy grail of modern physics. If we can crack it, a grand unified theory of everything would be within reach. Quantum mechanics and gravity are like sworn enemies. To make them coexist peacefully, scientists have tried every trick in the book. Right now, two main paths stand out. One is loop quantum gravity. The other is string theory. The idea behind loop quantum gravity is pretty straightforward. If matter is quantized, then spacetime itself should also be quantized. That means spacetime isn't continuous, but a network woven from extremely tiny quantum loops. In this model, when a star collapses into a black hole, spacetime doesn't curve infinitely. Instead, it bounces at the Planck scale. The singularity is replaced by something called a Planck star. It's no longer a point, but an extremely compressed yet still finite region. Over incredibly long timescales, this structure might even re-expand and release matter. String theory takes a completely different approach. It says the most fundamental building blocks of our universe aren't point-like particles, but tiny vibrating strings. Different vibration modes correspond to different particles. In the framework of string theory, black hole singularities don't exist either. Instead, there's an extremely dense bundle of strings, called a fuzzball. In this model, a black hole isn't a hollow structure, but a region filled with strings. From the outside, it looks just like a black hole, but internally its structure is totally different. Not only is there no singularity at the center, there isn't even an event horizon on the outside. Matter that falls into a black hole, that is, into a fuzzball, doesn't plunge into a singularity. Instead, it merges into the surface of the fuzzball. In this model, the black hole information paradox disappears naturally, because the information was never lost in the first place. It's just stored in the strings of the fuzzball. See that? Whether it's loop quantum gravity or string theory, both are telling us the same thing: singularities aren't real, they're just illusions of classical theory. But here's the problem. As nice as these theories sound, there's no experimental evidence for them. They're purely products of theoretical calculation. So is there a way to get rid of singularities directly within the framework of general relativity, without invoking quantum theory? Yes, there is. In 2006, physicist Sean Hayward made a tiny modification to Einstein's field equations. What he got was a black hole solution with no singularity, now called the Hayward black hole. At the core of this black hole, instead of a singularity, there's a region of de Sitter space, with strong gravity but finite density and pressure. A de Sitter core. De Sitter space is a type of spacetime with a positive cosmological constant. In it, gravity acts like a repulsive force. Deep inside a Hayward black hole, this effect becomes very pronounced. It counteracts the gravitational collapse of matter itself, and prevents a singularity from forming. Of course, the problem with this model is obvious. It just bans singularities by fiat, without telling you why nature should work that way. So it's more like a mathematical experiment than a complete physical explanation. Actually, the starting point isn't that important. Whether it's a Planck star or a de Sitter core isn't that important either. What matters to us is having no singularity. Our ultimate goal isn't to destroy singularities. It's to find the theory that makes singularities stop existing. Just like Einstein's relativity replaced Newton's absolute space and time, maybe one day we'll discover that there really is no singularity at the center of a black hole. Maybe it's a Planck star, maybe it's a de Sitter core, or maybe it's something we've never even imagined. And if black holes truly have no singularities, does that also mean the singularity of the Big Bang doesn't exist either? If the universe has no singularity, and there's no macroscopic something from nothing, then the universe has only two possibilities. Either it has always existed, or it cycles endlessly, like the conformal cyclic cosmology proposed by Penrose, where each universe, at the end of infinite expansion, quietly transitions into the beginning of the next universe. In this picture, singularities are smoothed out. Time no longer has a beginning or an end. Cycles, for the universe, are like breaths, one aeon after another, endlessly. What we call the Big Bang wasn't that moment when something came from nothing. It was just one ordinary evolutionary chapter in the universe's countless cycles.